Okay, moving on to carbonyl compounds tutorial question 6. Right, question 6 is a deductive question from 2015 A-levels. So we have these three compounds, pyrglugon, isopyrglugon, and piperitone isomers with the molecular formula C10H16O. Okay, so one look at this molecular formula, alright, because the carbon to hydrogen ratio is not 1:1, so it's likely to have no benzene ring. Okay, so that's something you need to think of in the first place. So all three isomers decolorize bromine water. So what are the functional groups that can react with bromine water? Aqueous bromine, alright, your alkenes, phenol, as well as your phenylamine. Right, so in this case, since there's no benzene ring, so likely we can deduce that this must be your alkene functional group, and the type of reaction is your electrophilic addition. Alright, and number 2, it gives an orange PPT. Okay, it's a condensation reaction, and we know that A, B, C must therefore be a ketone or aldehyde. Okay, and point number 3, none reduces failing solution. So failing solution is basically to test for your aliphatic aldehyde. Right, so many students were very confused that year about this being reduction. So recall, failing solution, actually the type of reaction is an oxidation reaction. Now, why over here it's written as reduction? So it's in terms of the perspective, failing solution oxidizes RCHO to RCOO minus. At the same time, failing solution is then reduced from copper in the +2 oxidation state to the copper +1 oxidation state where it's copper 1 oxide, grade PPT. Alright, so in this case, there is no aliphatic aldehyde. It does not undergo oxidation. Okay, point number 4, treatment with hydrogen gas and platinum catalyst. Alright, this is a reduction reaction. So before we move on to 5 and 6, let's pen together all our reactions first for 1 to 4 to see how we can get an idea of what these questions are asking. So this is the very first time you see the structure of menthol, which is how all three isomers A, B, and C can become. So which means if we know the functional groups in A, B, and C, and then we know how these functional groups can be reduced to menthol, we therefore will be able to know the structures of A, B, and C. So let's gather some information about what we have from A, B, and C so far. So A, B, and C are alkenes, okay, because they decolorize bromine water. Now we know that they can either be a ketone or aldehyde, but in point number 3, we know that there's not an aliphatic aldehyde, and therefore it must be a ketone. Alright, so far we know A, B, and C must have an alkene and a ketone. Okay, and after reduction, it becomes this. So it's quite obvious that over here we have a secondary alcohol. Okay, which means your ketone is reduced to secondary alcohol. This is the position of the ketone. So in other words, your compound here for your A, B, and C is likely to have a ketone over here, which will be reduced to a secondary alcohol. The question is, where is the alkene functional group? So where is the CC double bond? So there's a different position of CC double bond which you need to figure out. Okay, and this information is useful when we look at 5 and 6. Where is the position of CC double bond in the ring? Or is it in the side chain? So for 5 itself, we realize that it's quite complicated when treated with hot concentrated KMnO4. Alright, it's an oxidation reaction. So if you take a look at what reactions can what functional groups can be oxidized, it's an alkene functional group because ketone cannot be further oxidized. So you can see A gives compound D and E, B gives compound F and CO2, and C gives compound G. Now when you are given such an information, a quick way to sort of make sense of the information is to actually draw out something like this. Alright, so you can see A gives D and E, B gives CO2 and F, and C gives G. Okay, but there's not much information about all the compounds other than D, F, and G later on. So if you take a look at D, F, and G, they all give a yellow PPT with alkaline equals aldene. So D, F, and G. So what can we conclude? So the type of reactions with alkaline equals aldene, it's your oxidation. Iodoform reaction is an oxidation reaction. And basically we're looking out for this functional group, right? This structure group, your methyl ketone or methyl alcohol or methyl alcohol. Okay. But in this case, because compounds D, F, and G are formed after oxidation with KMNO4, it is unlikely that you have a methyl alcohol because an alcohol will be oxidized to a ketone. So likely D, F, and G has what we call the methyl ketone structural group. So because we're supposed to get the structure of A to G, and therefore we need to explain the observation, so let's have a go at writing the deductive statements first. Okay, if you have not done the deductive statements for this question, I suggest you pause the video now, try to write the type of reactions, and then identify the functional groups relating to the type of reactions. Then after that, you can continue on with the video to check your answers for deductive statements because they are marks accorded for the reasoning. So first of all, let's take a look at reaction 1. Decolorize brewing water. That's your electrophilic addition as I mentioned. Okay, because then we can include its alkene functional group. Then for the reaction with 2,4-DMPH number 2, it's the condensation reaction, and we conclude that A, B, and C have the ketone aldehyde functional group. So notice that I'm very systematic in terms of stating the type of reaction together with the functional group or structural group. Alright, I can do it in a tabular form so that it's easy to see the relationship. Okay, now we move on to the filling solution. So none of A, B, and C undergoes oxidation with filling solution. So A, B, and C do not have the aldehyde, or to be more exact, it's the aliphatic aldehyde functional group, and therefore A, B, and C must contain the ketone functional group. Now some of you may be thinking, why can't we consider the aromatic aldehyde functional group? Because earlier on we say that it's unlikely that A, B, and C has a benzene ring because of the molecular formula. So if there's no benzene ring, it is therefore not possible to have an aromatic aldehyde. So without having an aromatic aldehyde, without having an aliphatic aldehyde as indicated by the Fehling's test, therefore there is no aldehyde functional group. The only functional group in A, B, and C will be your ketone together with your alkene. Okay, so for number 4, we have treatment with hydrogen gas and platinum catalyst. In this case, we are looking at reduction. So alkene and ketone will be reduced to alkane and secondary alcohol. Okay, last but not least, we look at 6 first. 6, the reaction is oxidation, and therefore, as I mentioned earlier on, D, F, and G have the methyl ketone functional group and not the methyl alcohol. Alright, why can't we have the methyl alcohol? Again, I want to reiterate, because how is D, F, and G formed? D, F, and G are formed after oxidizing A, B, and C with KMNO4. So any alcohol group present previously will have already been converted to a ketone with KMNO4. So it's unlikely that D, F, and G can still have a methyl alcohol structural group after KMNO4. So therefore the focus should be on the methyl ketone. Now with this, we can then look at number 5, which is useful for us to know where the position of the double bond is. Now let's take a look at 5. When treated with hot concentrated KMNO4, we're looking again, like focus as I mentioned, is the alkene. The CC double bond will break, and then we'll get different products. So you can see, in this case, I break into D and E at 2 fragments. In B, I give CO2 and F, and C, I give only one compound G. Okay, so let's take a look. Now, upon strong oxidation of KMNO4, A gives 2 fragments. Now, we know that D must have the methyl ketone functional group. Because why? Earlier on we said D, F, and G have this structure because of the positive aldoprom test. So, after this structure and the molecular formula of C3H6O, how many carbons do I have left? If you look at this structure, we only have 1 more carbon, and to get the molecular formula, we therefore have CH3. So this is simply your propanone, and this is the methyl ketone structure that gives the positive aldoprom test. Now, if you look at this molecule as a whole and compare it with the structure of menthol, where must the double bond be then? The double bond must therefore reside over here, right? So that when you break, you get double bond O with the 2 methyl groups attached to it. Okay, so by this, we can therefore get the structure of the compound A. Alright, where as I mentioned, the secondary alcohol must be the ketone. Alright, the secondary alcohol must be the ketone, and the double bond is over here. Okay, so when you break this compound here, what do you get? You get a double bond O with a ketone over here. Alright, because these two groups over here are connected to carbon groups, you do not have to add any H or O to get a carboxylic acid. Okay, now moving on, when we take a look at compound B, B gives CO2 and compound F. Now recall, if a compound gives CO2 and F, this is an indication that B must contain a terminal alkene. Okay, so you can see it, me indicating terminal alkene here. What's a terminal alkene? Terminal alkene means that the CC double bond is at carbon number 1 and 2. So if it's a terminal alkene, alright, there is no more carbon on this carbon number 1 because that must be carbon number 1, right? So we cannot have any more C's here. It must be a H. If not, that will not be carbon number 1. So when you break a terminal alkene, what do you get? You get C double bond O, OH, and OH. And this is basically the carbonic acid H2CO3, which essentially is just CO2 plus water. And that's how, when we oxidize a terminal alkene, we will get carbon dioxide gas. And so, if we know terminal alkene, we take a look at the structure of menthol again. The structure of menthol is this, right, as given in the question. Where are the positions of the terminal alkene? So I'm going to highlight in green over here. I have one position over here, one position over here, and one position over here. Now, I want to highlight to you that these two positions are actually in fact the same. It doesn't really matter whether it's this or that because it's the same position you're looking at. So the question is now, which one then? Okay, so we take a look again. There's some information given to us about F. F must have the structure of CH3 C double bond O because we know that it's a methyl ketone. So therefore, it's not possible for the double bond to be here because if the double bond is here, when you break, you just have a ketone over here and CO2. You don't have a methyl ketone, and therefore the double bond must be over at this side. Okay, so you can see the double bond over here, and I convert my secondary alcohol to a ketone. When I break this, I'll get a double bond O with a methyl group over here, and that's how I get my methyl ketone together with CO2 as a byproduct. Okay, moving on to the last compound C. Alright, in C, you notice that okay, moving on to compound C, in the case of C, you can see that there is no loss of carbon. Okay, so C has 10 carbons, C10H16O, and after it oxidizes, there's no loss in carbon. Alright, it's important for you guys to know that in this case, it is unlikely that the CC double bond will break into two. Alright, so the only way where the CC double bond breaks into two and still remains connected is when the CC double bond is part of the ring. So when you break one part of the ring basically opens up and is still connected. And that's how you prevent a loss of any carbons. So the question is, in the case of menthol, alright, this is the structure given, right, of menthol. Where are the positions of the CC double bond? So we have one position over here, one position over here, one position over here, one position, one position, one position. Alright, so that's any position of the CC, the ring. Alright, but there are some positions that is not possible. Okay, why so? Because to start off with, this is not an OH, but a ketone. So, in fact, the correct positions are only these positions. 1, 2, 3, 4. These two carbons cannot have another double bond, the one highlighted in yellow. Because these carbons already have 4 bonds. Alright? This carbon in particular, I'm highlighting highlighting orange over here, it already has 4 bonds, so they cannot have another multiple bonds. So then 4 positions, 1, 2, 3, 4. Alright, position 1, position 2, position 3, position 4. Where you can have CC double bond. Now, importantly, we know that G also must have the methyl ketone functional group because, again, in the question it mentioned that G gives a positive iodoform test, a pale yellow PPT. So with that, we can only narrow it to two positive positions. Position where we have position 1, if you put a double bond over here, alright, you can imagine when I break this, I get a ketone, methyl ketone functional group over here, or I have my double bond over here. when I break this, I also get a methyl ketone over here. So therefore, there are two possible structures for C. So as I mentioned, position 1 and 2 are two possible positions. So this is position 1, this is position 2. When I break this, I get ketone over here with a methyl group. Okay, so you can see what happens when I break. So when I break here, over on this side, I get a carboxylic acid, but on this side, I get methyl ketone. So the methyl ketone will give a positive aldoform test. So similarly, over for position number 1, if I break over here, on this side, I get my methyl ketone, on this side, I'll get my carboxylic acid. Okay, so there are two possible structures for C, and therefore two possible structures of G. Right, so in general, this deductive question, if you can see, typically is 1 mark per structure. So you have A, B, C, D, E, F, and G. Okay, so 1 mark for each structure. And there are also marks given to the deductive statement. So there are 6 bullet points over here, so 6 marks for the deductive statement. So in total, this question is worth about 12 to 13 marks. Alright, so you can see the deductive questions are quite heavily weighted. Alright, getting the structure is tough at the first attempt, but with practice, you guys will get better in terms of the problem solving skills. Importantly, if the question ever wants you to give your explanation, you must be able to score these deductive statements. So remember the type of reaction together with the functional group. Okay, with that, I'm done with question 6.